is the surface point. It's actually an array value where the position is the surface point and the direction is the surface normal at that point. Having this vector, we can calculate the light angle, or even better, the cosine of the light angle, using the dot product from the surface normal at the intersection point and the light ray that we calculated in the previous line. If this angle, or the cosine actually of this angle, is 1, then the angle itself is 0, and that means that the two rays are parallel. In other words, the light is illuminating along the surface normal and the surface point gets full illumination. If the angle is 90 degrees, then the dot product, the cosine of the angle, is going to be 0. That means that the point doesn't get any illumination. And if the cosine of the angle is negative, that means that the angle is greater than 90 degrees, which means that the surface point is not facing the light source and cannot get any illumination at all. This is where we'll compare the light angle with 0, and if it's positive, we'll add to the diffuse lighting variable the light RGB color multiplied by the multiplier, which controls the intensity of the light, and multiplied by the light angle. This means that if the light color is white and the multiplier is 1 and the light angle is also 1, that means along the surface normal, then the final result is going to be a white color. If the angle starts getting greater in the direction of 90 degrees, then the color is going to fall off. Once we have calculated the light based on the light angle for all the lights that we collected and accumulated in the diffuse lighting variable, we can assign to the last surface color the result of the multiplication of the object's wireframe color and the diffuse lighting. At this point, we're not dealing with materials. We're going to implement this later. At this point, we are only going to use the wireframe color and the diffuse lighting model. In the end, we can return the last surface color. If there was no intersection with any of the objects, then the surface color is going to be returned as the background color with an alpha of 0. And if any object was intersected, the illumination of all the lights will be accumulated, multiplied by the surface color using the wireframe color, and then returned as the result. The alpha is going to be slightly bigger than 0, but because of all the multiplications could be more or less than 255. In that case, it's going to be correctly set to 255 in the end, in the clamping area of the code. At this point, we can also add a timestamp in order to know how long it takes to render. Let's define a variable st timestamp. St would stand for start time. Timestamp returns the current system clock time in milliseconds. Every time it's evaluated, it returns a newer value, which advances with the system clock of the PC. We're going to call the same function a second time at the end of the rendering and push the result into the prompt line of the user interface. We use the push prompt method. It expects a string. We'll build a string, ray script, and we'll add to this string the timestamp at the end of the rendering minus the timestamp at the beginning of the rendering, the whole result divided by 1000 in order to convert to seconds, since there are 1000 milliseconds in 1 second. Then the result converted to string and sec added to the end. We can go to the beginning of this expression and press Ctrl B to make sure that the brackets are correctly balanced. It looks like it's the case.